Tonight, I'm going to talk about probabilistic data structures. Understanding probabilistic data structures with 112,092 UFO sightings. I just thought it'd be a fun theme to use some interesting data to talk about some cool topics. And let's get this, there we go. And this my little introductory slide here. My name is Guy Royce. I'm a developer advocate with Redis Labs. And you can follow me on Twitter as @GuyRoyce. And you can check out my GitHub. All the code you see here tonight will be on GitHub, is already on GitHub. And you can check out my outdated website at guy.dev. Full disclosure, I do work for Redis Labs. There is some Redis content in this talk, but it's all free open source stuff. And this isn't trying to be like a big sales pitch or anything. It's just some of these probabilistic data structures are available in Redis as well. So, but it's all free, all open source. You can go take it home, play with it yourself. Nothing restricting you from doing that. So not trying to sell anything here, just trying to, I got a cool topic. They want me to mention Redis, right? and it is cool stuff. So, so this is an interesting number, 112,092. This is how many UFO sightings are in the data set that I got off of data.world. They've been gathered over, I'd say probably since about the 50s to the present day. And that's a lot of UFO sightings. And the data is fascinating and entertaining. If you are really interested in the UFO phenomena and have had experiences, then you could find that very enlightening. If you're like me and are a little more skeptical about UFOs, you can find it thoroughly entertaining. I think there's probably a good mix of all of that in there. But the data itself is fairly straightforward. There's several values to be had in there. You've got a summary of the UFO sighting. This particular one is 3 saucer-shaped ships. That's hard to say. Sue sells seashells by the seashore. High in the sky, metallic but no shine, rather dull gray, they hovered overhead in a V formation. This was in Salem, Oregon, so you got a city and a state. You've got a date time when it happened. This happened in September 15th of 1950 at 2 o'clock in the afternoon. The shape of it was disk, and so that's one of the data fields is shape. They have a duration. There's a link to the report. Those are always fun to read. The full text of the report, and then where it happened. And so there's lots of fun data potential here. The guy who gathered this data, his name is Tim Renner. He plotted them out and used clustering to determine where these UFO sightings tended to be gathered, and discovered that most of them happened within 50 miles of a US airbase. So that's a thing. He also made a bar chart showing which day of the year these UFO sightings were most common on. And by an order of magnitude, the most common day to spot a UFO was on the 4th of July. So is that a Roman candle? Nah, I doubt it. It's probably a UFO. So gloriously great data. And we're going to use this data to play with probabilistic data structures. But what the heck's a probabilistic data structure? I hadn't heard of them until, I don't know, about 6 months ago. I started looking into them. I'm like, these are really interesting. And I was putting together a talk. And so I thought, well, I haven't really run into these. Who has? And so I did a quick developer survey on Twitter and said, hey, have you heard of probabilistic data structures? 58% of the responders had never heard of them, which is, that's a big percentage. About a fifth of them had heard the term, but nothing more. Now, I wonder what percentage of that 22% had heard the term in the very question that I asked, because sometimes us engineers can be rather literal minded. But we're now sort of into the 4 out of 5 people at best have heard the term. 9% knew what they were, and only 11% of developers had ever used them. And so my guess is there's probably a lot of people here tonight that have not heard of them or don't know much about them. And so this feels like a topic that's which has a lot of learning potential. So anyone know what a probabilistic data structure is? Come on, Guy, tell me already. Well, I'm not going to tell you yet. I'm going to tell you first about deterministic data structures. And so in order to understand probabilistic data structures, they sort of have an opposite, which is deterministic data structures. Deterministic data structures are things that we're very familiar with as developers. You've got lists, you've got sets, you've got tables or dictionaries in Python, you've got tuples. These are things that in computer science class, you learned how to code these in C++ the hard way, and then you've never done it since. And because the language you're using provided them already. But they're deterministic, these familiar data structures, because you put something in them and then that something comes out. And they do that reliably and consistently. If you've got a hash table, a dictionary, and you put in city and state for the location of a UFO sighting, you can get city and state back out. And we pick these data structures for lots and lots of different reasons. They've got different performance characteristics, or they have the right metaphor for what we're doing. But I'm going to dive into hash tables and how they work inside, because a pattern that's used in hash tables is used in a lot of probabilistic data structures. And so if you look at a hash table, it's key value pair. It's a dictionary, right? So you put in a key, you get a value. You put in city, you get Salem back. You put in state, you get Oregon back. We know how to use these. Why are they called hash tables? Because they use a hashing function. A hashing function, we've probably all heard of these as well, but they take data and turn it into a number. And so you can take an arbitrarily large piece of data, a seed for a hashing function, run that through the hashing function and flatten that out into, say, a 64-bit integer or a 32-bit integer. And so that's what a hashing function does. And when I say hashing function, a lot of you are probably thinking, oh, like SHA or like MD5. It's like, well, yeah, those are hashing functions, but those are cryptographic hashing functions. And so they're slow because they're designed to create unique numbers, but to also have a quality of noise about them that makes them hard to reverse engineer. Whereas the type of hashing functions you would use if you were building a hash table would be something like FNV or murmur hash, where you want speed and uniqueness, but the speed's an important factor there. And so those are the type of hashing functions we'd use. And so what a hash table does is when you go to add something to it, is it takes the key, the city of Salem, the value, the string city, runs it through the hashing function, and then it does a modulus operation against the number it gets back that's equal to the size of a big array. So you've got this hashing function, we put city into it, we modulus at 10 because this is 10 elements high. And this is an array, it starts out, you start out at one size and it can grow over time. We're not going to talk about that. And then you've got a bucket where you store values. And so here, presumably, whatever number we got from city, modulus of 10 gives us a 1, and so we put it in indexed 1. And so this means that this the complexity of this operation is very predictable. It doesn't matter where in the hash table we go, it always performs the same. So it's nice and performant. And so this is how we add to a hash table. We get the 1, we say, okay, position 1 gets Salem. We come in and we put in state. We hash that, we get a different number, we modulus it with 10, and we get a 4, and so we put the state in position 4. Now, sometimes you'll get a collision. So when we put shape in, that ends up going in position index 1. The hash is different, but they both end in a 1. And so there's a collision in the array as to where to put them. And so the way this is typically handled, and there's lots of solutions to this problem, is you just put it next to it. This bucket is a linked list that contains the hash value and the value you want to return for each of them, and then it matches them up. And if they don't match up, it goes to the next one. And so after you find the index, then you have a linked list that you walk. And that linked list doesn't get usually beyond 4 or 5 items long. And then you go do this with several things, and then you've got this hash table here. Here's a fully populated one with the UFO sighting we were looking at. We've got the city, the state, the shape of the UFO, the date of the occurrence, the summary. And if we want to read from it, we just reverse that operation. We put in city, we get a 1. The 1 says, hey, it's this bucket here. We go through the linked list in that bucket, and we see if the hashes match. and it does on the first one, and so we return it. And so this is how a hash table works. Now, these deterministic data structures are often trade-offs in complexity. We've got time complexity, we've got space complexity. And when I say time space complexity, I really kind of mean in a big O notation sort of sense. But there's a lot of trade-offs here. So you might pick, say, an array list because it's fairly compact. Uses only as much memory as it needs, or a linked list, I'm sorry. But accessing items in a linked list is slow because you've got to walk that linked list to find the item. Whereas a hash table, its time complexity is better because it's fairly fast, because it's an O of 1 operation to find that which particular bucket you need to look in. But they tend to waste space. They're sparsely populated. And so they're slightly bigger from a space point of view. And so you're often trading off time and space complexity with these deterministic data structures, depending on what your needs are. And these things are particularly true when you're building systems at scale. If you're building a little mobile app, you're just using dictionaries because a name value pairs are a convenient metaphor. But if you're building if you're building Facebook, right, these things start really, really mattering. And so you start determining what kind of structures you want to use very carefully. And I said that these were in opposition, but they're not always in opposition, because sometimes there's some structures where they're good at one kind of thing, but not another kind of thing. And so you're trading off one kind of time complexity versus another. In the case of the linked list, accessing data in the linked list is expensive, but manipulating it, removing items from the linked list, is actually very performant because you're just moving pointers around. And so you're making trade-offs even within the time domain. And the same thing for space. There's other examples where you're making those same sort of trade-offs. And it turns out there's actually a third thing that you can trade off against, not just space and time. You can trade off against accuracy. You say, could I improve my access time? Could I make this more performant if this data structure was wrong 1% of the time? And would that be acceptable? Sometimes that answer is yes. Or this data structure uses 1/10 the space, but it lies to me sometimes. But it doesn't lie to me in a way that's harmful. It lies to me in a way that I can tolerate. That might be worth turning a terabyte into 100 gigabytes. And so that's the other type of complexity that you can trade off against. You can say, I want to save time and space, and I'm willing to sacrifice accuracy for it. And this is what a probabilistic data structure does and what it is. Here's an example of a super terrible, slightly, I'm going to call it an improbabilistic data structure, because it's a bad idea. But the hash table example, we don't have to actually do chaining, right? We've got the city here. There's Salem. It works as in position 1. And we go to update the shape, but we're not using chaining. We're not storing a linked list here. And so the city is now, the thing that's in the city position is now got the value for shape. And when you go and get the city back out, you now get disk instead of Salem. And so this is a probabilistic data structure in the sense that it's not reliable. Now this is a terrible idea, don't do it. Note the, oh my God, what have I done? Right? I wanted to make it really clear that this is definitely a bad idea, and it's probably a bad idea, right? So don't do these things, but this is an example of the sorts of trade-offs you're making. And this is actually a familiar trade-off because we've all used JPEGs. This wonderful picture of the Devil's Tower, made famous by Close Encounters of the Third Kind. This picture means something. And it means that it's a JPEG. And a JPEG, as you know, is lossy. They compress them down, but that compression loses a little bit of the data. And so this color of blue up here in the top left probably isn't the exact shade of blue that it should be for every single pixel. But it's good enough. You can't tell. The picture's still beautiful. And so you've made that trade-off of accuracy for performance. And so it's a little bit lossy, but good enough. So that's the idea behind probabilistic data structures. Clear so far? Cool. So this is my incomplete tour of probabilistic data structures. There's a whole bunch of them out there. I've got a list here of a few that you might want to check out, and I'm going to deep dive into 3 of them. Here are, let's see, we got a handful of them and what they're used for. And I'm going to go into the usage categories in greater detail in a bit. But we've got bloom filters, cuckoo filters. They are for checking membership. You can think of them as a set that has limited capabilities. You've got hyperlog log, and that will determine the cardinality. It counts how many unique items are in it. You got count sketch and count min sketch. That's a frequency that counts how many occurrences of a particular item are in them. You've got Q digest and T digest, which I don't know much about. Heavy keeper, which I know quite a bit about. We're going to talk about that in detail. And heavy guardians, and these are all about ranking things. It's not so much about counting, but it's saying put these things in an order. And it's okay if that order isn't perfect. Or maybe I only care about the top 12. And the rest of them I don't need to keep as close a track of. And so you can use a heavy keeper to do that sort of stuff. And then you've got MinHash and SimHash, which are comparisons. I'm going to go into detail on bloom filters, heavy keeper, and MinHash. The little red daggers here are things that are included with Redis. And with the single dagger, it's included with Redis Bloom. And so hyperlog logs is part of Redis. If you have a Redis install, it's there. Redis Bloom is a module. It's a plugin for Redis that you can install. And again, these are all free and open source. Some of them are source available and some are open source. To distinguish between the licensing, you can download them and use them. There's a restriction on the licensing for the source available that says, if you want to set up a service that then resells this as a service, you can't do that because we want to sell it as a service. But if you just want to install it in your own data center, you're welcome to do that. So that's what we mean when we say source available. But there's several out there to check out. And this one right here on the right is Redis Bloom, which has the filters in it. So I said I was going to talk about sort of like membership and cardinality and that kind of stuff. Membership is a really simple idea. If you think of a lot of these data structures as sets, membership is just saying, is the thing in the set? If I've got a set of states that UFOs have been sighted in, I can say, is Indiana in the set or not? If it is, then it is, and if it's not, it's not. We're testing for membership. Bloom filters do this. Cardinality is answering the question of how many things are in a set, how many unique items. So the set of all the names of states in the United States has a cardinality of 50. 51 if we count DC. And so that's the cardinality. Doesn't matter how many times you add Ohio to the state, to the set of states, it's only in there once. And so that's, it only counts once for cardinality. Frequency is how many of each thing is in the set. And so if I add Ohio 3 times and Indiana 5 times, then I can keep a count of how many times I've added those different things and get a frequency of how often these things occur in the set. Think of it, if you think of a set as sort of like a bar chart, that would be a good way of thinking about frequency. And we've got rank, which is where does the thing belong in the set. And I talked about that a little bit already. Oh, and we have similarity, which is really not about sets as much, but it lets you compare how similar a thing is to another thing. And for similarity, we're going to talk about MinHash and do some document comparison. So let's do bloom filters first. The little red asterisk means that bloom filters are part of Redis. Excuse me as I put a cough drop in so that I don't get super hoarse. A bloom filter tests for membership. Is the thing in the set or not? But a bloom filter lies, and it will either say, no, it's not in the set, or it will say, yes, it's probably in the set. And how often it is wrong is where the value comes in. If it gives you a false positive and says, this is in the set 1% of the time, that could be very valuable. If it does it 50% of the time, probably not quite as much. Cool thing with a bloom filter, they are of a fixed size. Once you establish one, they don't get any bigger. However, they have a limited capacity. You can exceed that capacity, but if you do, bad stuff happens because it will slowly start just reporting everything as being true. And so if you overfill a bloom filter, it will give you nothing but false positives. However, it is wicked fast. And we're going to go into the algorithm behind it, and you'll see why it's wicked fast. There just isn't much happening. So these are the parts of a Bloom filter. We've got a set of hash functions and their corresponding seeds. I'm using 3 hash functions because it fit on the screen. You could use more, you could use less. I wouldn't recommend using less than 1, or even less than 2, honestly. 1 by itself, there's a reason we have multiple, and it's to hedge against collisions. And we have a bit array that's of a fixed width. This one is 10 bits wide. In practice, this would be much bigger. And that bit array is the memory. And so if that's like 1,000 bits wide, then we're talking 256 bytes. No, 128 bytes, right? So it's very small. And then you've got your hash function seeds. You got to store those. But we're not talking a ton of space here. These are the 2 pieces. And when you go to add something to a Bloom filter, here we've got Megatron in the bushes. This is from a wonderful UFO site. It's my favorite out of the set. Not that I've read all 112,092. But this one is some guys out west had heard a sound. They'd stopped on the side of the road. They heard a sound in the bushes. It sounded like a transformer doing its thing from the 80s cartoon noise, you know, the sort of sound, which probably didn't come through the mic very well at all. But they and so they got in their car and took off, and these lights chased them down the freeway and everything, and it's a great story. And they called it Megatron in the bushes. And so you take that description, that account, that Megatron in the bushes account, and you want to add it to a Bloom filter. So you take that string, you run it through all the hash functions with all their seeds. And when you do that, you're gonna flatten out that story to, in this case, I'm using a 16-bit number, just for space reasons. You probably want a bigger one in practice. And then I do a modulus of 10. And why did I use 10? Because I have 10 bits. If I had 100 bits, I do a modulus of 100. If I had 1,000, I do a modulus of 1,000. And that gives me an index that I can then set in this bit array. And so, wrong direction. So I get 5, 0, and 6, and so I set bits 5, 0, and 6 to high. And now, if I want to read, if I want to say, hey, Bloom filter, have you seen Megatron in the bushes before? Then it goes through those same calculations, those same hashes, gets the same numbers, does the same modulus, and gets the same result, looks them up and says, yeah, they're all 1s. Everything's high, adds them together and gets a true back. And so Megatron in the bushes is probably in the Bloom filter. If you put another string in and one of them came back as 0, then that would return a false. We know for sure it's not in there because nothing's ever set that high. Now, here's another UFO sighting. This one happened here in Columbus, Ohio. I seen a UFO when I was about 13 years old. And it was in all uppercase letters in the UFO database. So good times. And so when we run this through those same hashing functions and get our indexes, we get 2, 1, and 6. And so 2 and 1 get set to 1s up here. And 6 has been set already, so we don't have to do anything. And so we've had a collision, but that collision hasn't hurt us. Because if we say, we run this string through it, we get those, we look them up, they're all 1s, and so it's good. If we go to the previous one, we get all 1s, so that's probably in the Bloom filter. And so that's the reason we have multiple hashing functions, is so that when we run into a collision like this, it doesn't sync, it reduces the false positives. And so this is good. If we had just one hash function here, then a collision would immediately make it so that we couldn't really be sure. We'd have less confidence. That it makes the false positives more likely. Now, we got another sighting here. Investigators from the Bigfoot Field Researchers Organization observed a glowing green-blue sphere. And this is a total collision. 0, 1, and 6 are the numbers we get out of the calculation here, and all of them have been set to true already. And so the Bloom filter doesn't change. None of the bits have changed their value at all. It's exactly what it was before. We've added it And if we ask the bloom filter, has this been seen before, it'll say probably. But if we hadn't added it and we asked it, it also would have said probably. And so this could be a false positive or maybe not. This is where the probabilistic nature of these things comes in. And it would depend on the order you add these things in as well. So it's very non-deterministic. And so this is, in essence, how a bloom filter works. I mean, not in essence, this is how a bloom filter works. And how the false positives can manifest. You might be wondering, how do we determine how big to make a bloom filter? There is some math for that. You're welcome to do this math. I don't want to, but you can solve. I'm told the way to do this is you've got these 4 variables here. You want to solve for p. You want to find out what's my false positive rate, and you probably have a specific false positive rate you want. And so you can do algebra to figure all this out. But the recommended pattern that I saw was pick an m for number of bits, just guess. And pick an n for number of items, which you're going to know. It's like, I want a bloom filter that's going to hold up to 10,000 items. And solve for k. K will then tell you how many hashing functions you need. It will allow you to solve this function and will give you a probability of a false positive. And if that number is too high or too low, adjust the number of bits and cycle through that till you're happy with what you get. So that's how you can compute this manually. Of course, you can just use Redis, right? And so here's the Redis command. You can call bf reserve, and you can just say, I want this error rate and I want this number of items, and it'll figure it all out for you, and you can just use it. Redis Bloom is super easy to use. Once you've reserved one, you just add things to it. You'll notice, I think this is kind of neat. We add disk, we add light, and both of those return a 1 because they've modified the bloom filter. They've modified the bit array. But down here, we add light and teardrop. Light did not modify the bit array because it had been added before, so it returns a 0. So to tell you whether what you've added is there already or not. And so you could actually monitor that if you wanted to and keep track of that and say, no, I know I haven't added this before, so that is now on my list of false positives. Or you could just be happy with it and leave it go. I think a cool use for bloom filters is managing users on like a large online service. If you've got, say, 1 million users and someone's typing in their username that they want to use and you want to see if it's taken or not, you can run it. You could have a bloom filter full of all the taken usernames. And then if I type in, Guy the Destroyer into my WoW username that I want to use, it can look in that bloom filter and say, well, it's probably taken, so you can't use that username. And that's way more efficient than, say, trying to query, select username from users where username equals this, with 10 million records. So that's a good use case for bloom filters. But BF add here, you got BF mad for multiple add. To check for existence, you just say BF exists, and it will give you a 1 or a 0. 1 meaning probably, and 0 meaning definitely not. And so that's bloom filter. Any questions so far?
I haven't seen anything necessarily. I'm glad you gave me an example of why I would use this.
Yeah, it's a real simple example. I wrote a blog post for that example, but there's no limit on the size of the data because we're hashing it. And so you could even say, have I seen this content before? Like you could run the bytes of a PNG file through a bloom filter and then say, have I encountered this PNG file before? So you could use it for finding duplicates, probably.
Yeah, if anyone has a question, make sure to just throw it in the chat down at the bottom, just because there's a bunch of people. I don't want anybody talking over each other.
Yeah. Okay, so that's bloom filter. Let's look at MinHash. MinHash is not something that Redis does, but I think it's kind of cool. And so I wanted to talk about it. What MinHash does is it can determine similarity between documents. And so you could use this for like plagiarism detection, or maybe web crawlers trying to figure out whether they should re-index content or not. Has this content changed enough, or I've seen it before? enough that to justify re-indexing it. And it uses that using this idea of Jaccard similarity. And Jaccard similarity is a really simple calculation with sets. And so here we have Sculder and Mully, face swapped X-Files stars. Excuse me. And I've got a set here of Sculder's states that he's seen UFOs in. So California, Nevada, Oregon, Wyoming, New Mexico, and Ohio. And then Mully over here has her 6 states: New Mexico, Ohio, Florida, Kansas, South Carolina, and West Virginia. And all you do is you take the cardinality of the union of this entire set, in other words, the count, the number of items in it, and you get the cardinality of the intersection, and you divide them. And so intersection divided by union is going to give you a ratio. In this case, it's 0.2, 20%. So these sets are 20% similar. If the sets both contain the same thing, the intersection and the union would both be the same number. And so then you would have a Jaccard similarity of 100%. So it's a fairly easy calculation. And you can apply it to lots of things. But one thing that it's really useful to apply to are documents. And so what you could do is you could take a document and you can turn it into a set. And then you could do the Jaccard similarity on the sets of the words in one document versus a set of words in the other document and get a number. But if you just used individual words, well, that's not going to work very well because we're all using the same words. And so you're going to get similarity that basically says they're both English.
Yeah.
And so what you can do instead is you can, instead of looking at a single word, you can look at 2 or 3 words, a bigram or a trigram. And trigrams make the most sense. And you can overlay them. So you can do shingled trigrams. And what this is we take 3 words and we put that into our set. We notice 2. Then we shift over 1 and then notice 2 hour. And so we're pulling out overlapping trigrams. This is kind of like when you're doing convolutional neural networks for image processing, where you sort of got this sliding overlaid window that's looking for pattern matching. It's a very similar sort of process. And so here's to our left, and then you go through the whole document and you end up with a set of trigrams that are overlaid, like shingles on a house, hence the name. And now we've got a set of all those in that document. And we could compare Sculder and Mully's reports to Skinner and see how similar they are, so that we can see if they're telling the same story or not. And so I've just taken these sets that set I created and took some off the top and bottom of each one so that they're mostly similar, but they're not exactly similar. And I've come up with a union of 11 and an intersection of 7 for these two reports, which gives us a 7 divided by 11 gives us 0.63 repeating. 0.63 repeating would probably be a better way to say that. And so we can see that they are roughly 63%, 64% in agreement. The reports are, so that's good. Skinner is happy. But it turns out this process is kind of inefficient. If you've got to do this set comparison against strings and you've got lots of different documents all over the place, this starts getting, performance becomes a problem. And so MinHash solves this by hashing these sets. And so here we got Sculder's report, these trigrams. And what we do is each single trigram here, we run through n number of hashing functions. So we run all of these trigrams through the first hash and get a collection of numbers. And we run all these trigrams through the second hash and we get another collection of numbers. And we do that for all of our hashes. We have 3 here. And then we take the minimum number in that set of numbers, and that is put over here, and we get a set of all the minimums. So it's the minimum hash for each hashing function for all the trigrams. And so I'm going to say that again because it's a little hard to follow because there's a lot of steps here, but we're taking each and every single one of these results in a number in these columns. And then we take the minimum number from each of these lines. And this becomes a new set that we can then do Jaccard similarity calculations against. So we do the same thing for Molly. We get a different set of numbers. Well, many of these numbers are going to be the same because these trigrams are the same, and some of them won't be. And here we end up with a set that looks like this. We got 23, 143, and 102 on the left for Sculder, and Molly has 23, 143, and 101 instead. And so when we do the math, we find out that they're 50% similar. Now this is not as accurate as the number we looked at before. If we look here, we got 0.63 repeating, and we got 50%, 0.5. But part of the reason of that was because we only had 3 hashes. If we had more hashes, we could increase that accuracy. I just put 3 because it was convenient. But the more you have, the more granular your number is going to be. But then the more processing it's going to take to create this set. Now these sets can be stored and saved, so it might be worthwhile to have more hashes. And then when you encounter new documents, you can do the same thing. And then doing the set, the similarity calculation against a handful of numbers versus a whole host of trigrams, it is a huge time savings. Because if these documents were, say, 100 pages each, and we ran them through 5 hashing functions, we'd end up with 5 numbers, as opposed to, thousands upon thousands of trigrams. And so this is a big performance save. Yeah.
There is a question about examples of hashing functions. Or is that something you may show later, or is that?
No, I don't have any hashing functions. I'm not going to go into the hashing functions themselves. There's plenty of them online. I actually did implement all 3 of the probabilistic data structures I'm talking about today. Unfortunately, for the Python meetup, I implemented them in JavaScript. But you can go look at the implementations. And when I did that, I just used NPM packages that implemented the hash functions for me. Lots of times they're not very complicated though. And so you can Google that and find some basic hashing functions pretty easily. But I'm not going to go into any of those in detail. One thing worth noting though is that with these hashing functions, this is not an FNV, and this is not a murmur, and this is not some third one. This is the same hashing function with different seeds. We're not using. I mean, you could use a variety of hashing functions that'll work, but the intention here is that we're using seeds. Odds are you're going to want to control the number of hashing functions you can have. Seeds are an easy way to do that. So that's MinHash. Any questions on MinHash so far?
No, I think we're good.
Cool. Okay, so let's get to the showstopper, the top K, the heavy keeper. Top K is actually a problem. Heavy keeper is an algorithm that solves it, a probabilistic data structure that can help solve it. So top K is a ranking problem. Right? Give me the top 5 most clickbaity articles that you won't believe, right? And when I first saw this, I'm like, top K what? What's the K? Well, K, I mean, it's just statistics sort of sense of K being the number you're looking for. My sort of provincial instincts were to say, well, give me the top N whatever. That's really all we're saying here when we say top K. So Heavy Keeper ranks the top K items. It does that using 2 structures, a min heap, which I'm not going to go into detail on. Min heap is a deterministic data structure that's, if you've taken computer science, you've probably had to code and have buried the memories of doing so. And the Heavy Keeper, which is honestly the interesting part. The min heap has a fixed size and keeps track of the maximum numbers that are in it. So we can either use the min heap to keep track of, like, the top K things are stored in the min heap. And Heavy Keeper, the thing that's coordinating between it and the Heavy Keeper makes that work. The Heavy Keeper is using hashes again, like a lot of these do. and it's got a two-dimensional array of buckets and hash functions, and we'll get into detail there in a minute. There's our min heap. I sort of mentioned that already. So this min heap has commonly used words in UFO sightings, and it's got a count. So the most common one is disk, and then sky, then light, or then dark, then light, then object. And the heavy keeper will find new items, and if it's bigger than the one that's here, it will push it onto the min heap and pop off the 54. And if it's smaller than the 54, it just throws it away. And so that's how the heavy keeper uses the min heap. The heavy keeper itself is made up of, again, hashing functions and seeds. And then you've got these arrays, an array for each hashing function. And those arrays are indexed in the same way that the Bloom filter was and the same way that the hash table was. The buckets have a hash, not the modulus hash, but the hash itself. So, and then it's got a counter. And when you create a new heavy keeper, it's nice and empty. All the hashes are null, all the counts are 0. So we got a nice empty heavy keeper. And when we go to add a value to the heavy keeper, it's going to start counting them. So it's got to count them to know whether there's more of them or not. And so we're going to put the word object, which is a common word in UFO sightings. It's also a common shape, into these hash functions. We're going to get these numbers. We're going to get these hash results. 5062, 3111, 1442. And we're going to modulus them by the width of these arrays to get the index again. And so here we get 2, 1, and 6, or 2, 1, and 2. And so we go to them, they're empty. So we populate the hash, that null, we replace it with the result of the hash, and then we increase the count by 1. So it goes from 0 to 1. So we bumped it up. Easy so far. We're just filling in these values here. Before it was null, now we have a 1. If we go to add the same value again, then of course we get all the same indexes again, and we have the same hash. And so it takes 5062 in position 2, goes over here and says, yes, the hash is 5062 in position 2. So let's increment the count by 1. So now we know that it's been done twice. And we do the same thing down here, and we do the same thing down here. So if we add object twice, unsurprisingly, we have a count of 2 for each of these. So the count goes up. And if we want to query the count, we can do that same calculation, find the locations, check the hash, get all of our numbers here, and get the maximum number out of that set. Now they're all 2s, so it doesn't matter. But if we want to query that count out, that's how we do it. Now, if we add a different value, let's add the value light, another popular UFO shape. And here in green, you can see that the index said shove it here. Excuse me. Shove it here and shove it here. And so those were unoccupied. And so we just set them to 1 and we populated the hashes. However, down here, we've got a collision because this space is occupied and 1352 and 1442 aren't the same. So who wins? What do we do? This is where heavy keepers are interesting. What we do is we start doing some math. And we calculate a probability of decay. And in our case, this comes out to 0.907. And that is the chance that we're going to go ahead and decrease the number. Now, we're going to decrease it, but we're not going to remove it. And so this number is calculated by taking the rate of decay, which is a number that you pick when you set up the heavy keeper. It needs to be greater than 1, but about 1. And so I picked 1.05. And what you do is you take this magic number and you take it to the power of negative the count. So we've got 2 items here. 1.05 to the power of -2 is 0.907. Now, if there were a lot of things in there, say 1,000 things or 10,000 things, this is going to be a really small number. But if there's very few things in there, it's going to be a fairly large number. And so small things are more likely to get kicked out of the heavy keeper. Big things are more likely to stay put. And this is why it's called a heavy keeper, because it keeps heavy things. And they use the terms elephant flows and mice flows. If there's a mice flow, they're likely to get stepped on and pushed out of kicked out. But the elephants hang around. It keeps the heavy things. And so as the data is flowing into the structure, the heavy things keep getting heavier and heavier, and they get momentum and they stay put. And the smaller things can't dislodge them. So that's how this thing works. And so I'm going to go ahead and assume that given a 90.7% chance of decaying, that probably happens. And so this was a 2, and now it's a 1. Now 1352 never gets stored. But the result of doing light was stored in the other 2 here. So when we go and read light, we go out and we find it here, and we find it here. These numbers match. It finds a 1 and a 1. And in here, it doesn't find it at all. But we're good because we've got multiple arrays. And so it's like, well, we got a 1 and a 1 back. So we'll take the maximum value there. And it's 1. And so it's still correct. And so this has decayed some, but this one is still able to be queried. If we go and query object, which is the thing that we initially added to here, we can still go query it, and we get these 3 values here, but this one's now 1 less. And so we take the max of the 3 values we get back. It's still honest in reporting that 2 items are there. And so one of the effects of the counting in heavy keepers is they're never more than how many items have been added, but they're often less than, because these numbers go up and get pushed down and go up and get pushed down. But counting isn't the primary purpose of the heavy keeper. Ranking is. And so when we add things and these numbers change, we're constantly updating our min heap. And that's where when we ask, hey, what are the top 5 items, that it stores those results. And so that's what we interrogate. And of course, Redis supports these. In Redis, you can say top K reserve. You can give it a key. You say, I want to store 3 things. I want the top 3 UFO shapes in UFO sightings. You can give it a width. That width is how wide that heavy keeper should be. The depth is how many hashes you have. And that decay is 0.9. They've just taken that 1.05, and in Redis, they've taken the reciprocal instead. So they're just doing the math slightly differently. That works out to be, I think, 1.1 repeating. And so you can set this up in, this way. And then to use it, you can add things. We add a disk. We add disk and teardrop for common shapes. We add light, disk, and teardrop. If you're counting, that means disk should be in here 3 times. Teardrop should be in here twice. And light should be once. When you go to query it, you can say, is disk in the top K? And it will say, yes, it is. If you said, is some other thing that we didn't add, is, cigar, in the top K, it would say no, because it hasn't seen it before, and it's not in the top K. You can do the count on teardrop and get a 2 back. And if you do a top K.list on the key, you'll get the top 3 items, because that's what we set it up for. And it puts them in order. I have noticed that sometimes the order is wrong if you have really, really small counts, because I think the heap and the heavy keeper get out of sync. Because the heap's kind of decreasing numbers, or the heavy keeper's kind of decreasing numbers sometimes. That's just a behavior I've noticed. When there's large quantities, it's very consistent.
We have
It
one
is a
question.
problem. Yeah.
So does number of hashes determine the level of accuracy?
Well, it's the number of hashes and the width are always a trade-off, right? So if you add more hashes, the collisions don't hurt you as much, but then you're taking up more memory, and so it's part of the trade-off calculation. And if you're wider, you don't get collisions as much either, because you've got more indexes. But again, you're taking up more memory. The compute's faster when it's wider, And it computes slower when you add hashes because you've got to hash each one. And so you're making trade-offs in that sort of way. And then both of them create a memory footprint.
Mm-hmm. Now,
And
is there also a way to know the statistical accuracy? Like you say that they can decay, or the numbers may not be accurate, or they're probabilistic. Do we know to what confidence level?
I know that we've done benchmarks against the one in Redis, and we got like 99.9% accuracy. And it was faster than using a sorted set and took up about 100th of the space. So it was a good trade-off. And they were counting the words in War and Peace, trying to say what's the top 10 words in War and Peace. And so I know it's good. I don't know exactly what the formula is. I actually had to get how this worked. I had to read a really, really, really boring white paper. And I have a link to that. And if you want to read the really boring white paper and you can find that out, I would love to add it to my slide. So if you could do the work for me, just joking, but yeah, I don't know what the actual, I don't know what that formula is to calculate that probability. I'm sure it exists, and it's probably buried in that white paper. But that's a great question.
One more question before we go. Does the app consuming this need to handle the miss case in some special way?
The miss cases as in like not in top K?
Says Robert.
Robert can unmute if he wants to ask.
Yeah, go ahead, Robert.
If you're comfortable doing that.
Hey, yeah. Sorry, yeah, I guess just talking is easier. Sorry, I'm new to the probabilistic idea here, so I'm still trying to wrap my head around it. By miss, I meant where something had decayed and you're getting back perhaps an incorrect value.
The counts can be incorrect. If something's decayed and it's not in any of the arrays anymore, then it was small and it got pushed out by bigger things, and so it's not in the top K, and so it doesn't keep track. It doesn't care about keeping track of it. And if it's small in the beginning of your set but shows up in greater frequency later in your data, it will get re-added and then start pushing other things out and then make it into the top K again. So I think that answers your question. Things can get kicked out that are small, and once they get kicked out, we don't care anymore. And if we do care, and if they are common enough that we care, they'll get added back in. That's sort of the idea with the heavy keeper. Does that answer the question satisfactorily?
Yeah, I think I get it now. Thank you.
Yeah.
Yeah. So there was another question about the procedure when the count reaches 0. Does a new hash replace it? I assume we're talking about the tree, so some new value would then. Yeah.
If it's got 1 and it decays, then it gets swapped out. I'm pretty sure it gets swapped out. You could probably implement it either way and it would work. Like you could just say, when it gets to 0, remove it, but don't add this other thing. But that seems really unsatisfying. And there's actually a little table that explains how it works in the white paper, and I coded it and I know it works, but I don't remember which way I did it now. But I don't see any reason why it couldn't work either way. I think if it's 1 and it gets bumps, then it probably gets replaced. That makes the most sense to me. We can check the white paper afterwards if you really want to know. But yeah, I think it could work either way. Any other questions?
I think that's it for now. Probably should move along.
Okay. Well, I have a demo
Awesome.
where I've used top K, and so I need to switch which monitor I'm sharing. Probably should close my email. I need to find. What can I need to get to Zoom. I need to stop sharing. That's what I need to do. Can I switch sharing?
Yeah, I think if you click share again.
Yeah.
Actually, there's one more question here.
Yeah, sure.
Yeah, after spending some time working with these data structures, do you start seeing uses for them everywhere?
You do start seeing uses for them where you wouldn't think. There's a lot of really good ones, like counting things. Hyperlog log is really useful and really easy to use. because it will just tell you how many unique items have been added to it. Are you guys seeing my screen now?
I see a screen that says the number 2 on it.
Okay. There we go.
Sorry, Calvin, did you just say you saw guys number 2?
I'm terribly sorry.
All I see is Guy now, actually.
Okay.
I'll make no comment as to which number I'm seeing anymore.
There we go.
Yeah, it says demo. It's in your PowerPoint.
Excellent. Okay, we're on the right slide now. And are you guys seeing the Zoom interface at the bottom?
We see your terminal.
Okay, you just see the terminal. Okay, good.
Yep, just terminal.
Good. So Zoom's doing what it's supposed to. I'm sorry, I was distracted. What was the question? Was you start finding use cases for them? Yeah, like hyperlog log's really cool because it counts things, and it can count a ridiculously large number of unique items, like number of protons in the universe sort of numbers, but only takes up 12K. And so it's like, well, I need to count how many of a thing there are, but I don't care to ask what things were added to it. That's a really good way. So like if I wanted to count users who had interacted with a piece of content, I could just start shoving them in there. And it'll be a little bit wrong, but not terribly so. And it's good enough, right? YouTube's using these sorts of algorithms for like video counts and stuff like that. So you do start seeing a lot of patterns for them. So, okay. So I have built a fun little app. I've got Redis running here, a little Docker image, Redis mod. It's Redis with a bunch of modules installed, including Redis Bloom. And I've got some Python code to make use of it. And I'll show you the Python code. Actually, I'll show you the app. I'll get this thing running first. Now let's look at the code. So we've got this little app. This is some JavaScript code here. It's just a little web app. It hits a simple HTTP API to get word counts and shape counts of the top 10 most used words and shapes in UFO sightings, which is kind of fun. We got app.py here. This is the Flask app that I sort of cobbled together. Here's our two things. If you hit the /shapes route, it will ask Redis for the top K count for UFO shapes. And it will ask, and for the top K list here. So we get the list, we use this comprehension to then query all the counts. And we do the same thing for words, for the top 10 most used words. And we got this little static route here that I set up to pull in all my HTML, JavaScript, and all that kind of stuff. Not really production code, but good enough for this sort of demo. The really interesting code is over here. And this is the where I build this data set. Right, I'm gonna go ahead and launch Python app.py. And so it's going to try and hit a, it's hitting Redis right now, and the key's not found. So it's complaining. But it'll keep complaining. It won't crash. So when I run build.py, it'll start populating Redis. And so what this does is, get my Redis client, I'm using Pandas and NLTK. And so I'm taking this UFO data set, I'm taking the account, and I'm parsing out all the words. And I'm using stop words so that the top 10 UFO words aren't a, and, the, or, of, and that kind of stuff. They're just, regular words. They're more meaningful words. And I'm using the tokenizer in there as well. So I get my client set up. I set up a couple of top Ks here using the Python top K reserve call here. One for the words and one for the shapes. And then I return that client. I read in that CSV file here, and I drop everything except the text of the eyewitness account and the shape of the UFO. And then I process that data. I go over the rows, I get the shape, I get the words, I parse the words using NLTK. I pull out anything that's not alphabetic, because NLTK will take like periods and punctuation and make those words as well. And so I'm just tokenizing the word. Then I got a little comprehension here that turns it into the words I want. And then I just start adding them to the top K. And that's all this code does, is it just tears through these words, pulls these accounts, pulls them apart, starts adding them to Redis. So it's adding a lot of data to Redis. And when I run it, let me bring up, okay, so this app is out there hitting it right now. It's not doing anything. When I run Python, it's better than the Python typo that everyone always makes. Build, if you haven't gone to python.org, don't. So now we're gonna start reading that file. And so it's tearing through the words and it's giving us a status here of all the words it's found. And if we go back to the web app, we can see it's now hitting every couple seconds and it's finding the top 10 words. And these counts are going up fairly quick. And we're starting to see some patterns of words that would make sense in UFO sightings: light and lights, object, craft, sky. And you can see they're moving around quite a bit. And then the top shapes here is stabilized a little more quickly because it's a smaller data set. Eventually this will sort of stabilize and actually give a fairly robust thing. My poor little MacBook here is just trying so hard. Hopefully you can't hear.
I was going to hope that the truth is not David Hasselhoff.
No, it's not. The truth is not there. And so this is doing what it does, right? If we go back to here, we can see the words as it sorts through. We've done about 400 some odd sightings so far. If we look over here, we can see that our JavaScript keeps pinging the Flask server. And over here in Docker, it's just sitting there, not even caring. So that's our little demo. All of this code is available on GitHub. You're welcome to check it out. Let me go back to my slides here. Actually, let me kill this because it's making my fan go crazy. So all that NLTK stuff is just like, I'm sure, just making my computer. There we go. Site cannot be reached. Okay, so get back to this. I'm going to present this again, and then I need to switch my monitors, and I'm going to share that screen. There we go. So some resources if you're curious. We've got Bloom filters by example. This was a great blog post where I learned how bloom filters work. The guy did just a fantastic job. His little embedded app and everything to show you how they work. If you want to do that math that I showed you earlier, there's a bloom filter calculator, which will show you how to do that math. This is the MinHash tutorial that I learned from. It was really good as well. This is the white paper that I was talking about earlier. If you want to go read the white paper. It's actually not as terrible to read as I make it out to be, but it's still a white paper from like an academic math point of view. So it's kind of dry. The UFO data is this is Timothy Renner's UFO sightings data. He screen scraped the National UFO Research Center, his website, to gather this data. So lots of great stuff there. And there's the National UFO Reporting Center, I guess Reporting Center, not Research Center. Redis Bloom, if you want to get Redis Bloom. And then here's a blog post on Top K. It talks about the War and Peace example that I mentioned earlier. This link here will have, this is where all the code's at. You can get a link to the slides and go play with this yourself if you want to look at the abstract. This is the link if you want to grab a link. This is the one to grab. It'll have all of those other links on it. So that's all I've got. Again, I'm Guy Royce. Please follow me on Twitter so that I can feel like a human being that has enough followers, which will never be enough. But and check out my stuff. And thanks.